All right, this is our last day of notes for AP Pre-Calc. We need to talk about how to find relative extrema. So that's a relative max or a min for values of R. So this is just like what we did in chapter 1. Anytime a function, in this case R, goes from increasing to decreasing, you're going to have a relative max or a local max. Sometimes we use that terminology. And anytime that R changes from decreasing to increasing, you're going to have a relative or a local minimum. And we just talked about yesterday how to decide if R is increasing or decreasing. You just use a table of values and see what's happening. You do have to be careful. I would say don't use the polar graph because it's easy to look at. Let's say we look at I don't know, a cardioid or something. It's easy to be like, oh, that's a relative max and that's a relative max and that's a relative min. And have we really done the math to double check on that? We might be right about that, but especially with rose curves and things, this might look like a relative min, but how do I know whether it is or not? It might not be because R can be negative. So don't use the polar graph because negative R's mess things up. All right. Also, I have something to exclude from my packet here. So so if a polar function changes from increasing to decreasing or vice versa, then we have relative extremum. That's what we're talking about, corresponding to a point that is relatively furthest or closest to the origin. So that I want to take out that part. The relative max is not necessarily where the graph is always going to be furthest from the origin, and the relative min will not always be where it's closest because, again, negative R values kind of mess things up. You could have a relative minimum at a petal, the end of a petal where R is negative, and you're definitely not closest to the origin if you're right here. So let's just cross that out. Um, we're just fighting relative max, relative min. If we want to know if a graph is close to the origin or getting closer to the origin, we will use what we learned yesterday: the sign plus or minus of R and the fact that R is increasing or decreasing. Okay, so determine if the polar curve has a relative extremum on the following intervals. So that means, is there a relative max or min? And if it does, classify it as a local or relative maximum or minimum. Right, so how are we going to do this? I put a graph here in case you wanted to look at what was going on. But again, we're just going to take a look at this and I'll do the graph in a minute. Okay, so here's our function. Here's our interval. I'm going to start with a table. So we're plugging in a -3 minus 2 times sine theta. We start at each end of the interval. These could be parentheses too. I can't, I think it could be interchangeable. So we're going to start with pi over 3, and we get -3 minus 2 times the sine of pi over 3 is radical 3 over 2. So this is -3 minus radical 3. Not a nice value, but again, we don't have to graph, so we don't care whether this is nice or not. The point is, this is negative. Okay? And then we're looking at what's next. We're on pi over 3 to pi over 4. So I'm just going to remind myself, here's pi over 3 to 3 pi over 4, not pi over 4. So, okay, what nice angles do we have in between here? So next would be pi over 2. -3 minus 2 times the sine of pi over 2. So -3 minus 2 is -5. So far, R is decreasing, right? On this interval, R is decreasing. It's going from -4 point something to -5. And then we're going to plug in 2 pi over 3. So -3 minus 2 times sine, again, is positive radical 3 over 2 at 2 pi over 3. So now we're back to -3 minus radical 3. So from -5 to -4 point something, now R is increasing. Because remember, with negative numbers, the closer you get to 0, you're increasing. And then we can look at the last value, which is 3 pi over 4. So that's -3 minus 2 times positive in quadrant 2, radical 2 over 2. That's -3 minus radical 2. Now, this is also -4 point something, but it's less. This might be -4 point, I'm making this up, -4.2, and this could be negative 4.1 or something like that. So from this point to this point, r is still increasing. So actually, from pi over 2 to 3 pi over 4, r is increasing. And then from pi over 3 to pi over 2, r is decreasing. All right, so what does that mean? R just went from decreasing to increasing. That means that there is a local minimum. I always have to sketch this out to keep this straight in my brain. There's a local minimum at, where's the breaking off point? It's pi over 2, right? The value for r will never exceed negative 5 because the largest value for sine is 1. So this graph can only get to negative 3 plus or minus 2. All right, so there's a local minimum at theta equals pi over 2. And then we need to justify why. So I would just say because r changed from increasing, no, it didn't change from decreasing to increasing at this point. This is good prep for calculus. You might do some work over here, and a lot of times for calculus, depending on what you write over here, they may or may not actually grade it. So I'm not sure for our AP Pre-Calc exam, does this table count as work? I would suspect that it does, but just in case, I want to reemphasize why I'm making that conclusion. Okay, now what if we looked at this graph? Because I think, again, the graph can be misleading sometimes, but we'll just have to see what's happening here. So, all right, so if we were to face pi over 3 and go back, what did I say? Negative 4 point something. So 1, 2, 3, 4 point something right there. And then when we face pi over 2, we go down 1, 2, 3, 4. We go backwards 5. And then we're at 2 pi over 3, and we're going negative 1, 2, 3, 4 point something. So see what's happening here so far. The curve would be mapping like this. All right, so what is happening to r? This is a minimum, and I know that's like, well, yeah, because that is a minimum, a relative minimum if we were looking at a regular function. But what I had you cross out was just because it's a relative minimum does not mean that that's where the graph is getting closer or is closest to the origin. That's not true. Actually, this is the point where down here, this is a point where the graph is furthest from the origin because r is negative. So just something to be careful about. We're not getting into closer or further from the origin. All right. What about rate of change? This is the last thing. Again, we spent a lot of time in chapter 1 talking about rate of change and in other chapters as well, looking at different functions and calculating average rate of change. So remember this. You have some sort of curve, some sort of function f of x. The average rate of change, which we were calling AROC, is equal to the change in y over the change in x, right? And officially that's f of b minus f of a over b minus a. And if you had to interpret the average rate of change, you would say the average rate of change tells us, at least this part, f is you pick increasing or decreasing, whether the AROC is positive or negative, on an interval by approximately whatever number the average rate of change is. And then you say y units per x unit. That's always in context. So the maybe average rate of change is a speed or a velocity. The velocity is increasing by 10 miles per hour, something like that, on average. Oh, always on average. What about when we have a polar function? It's not just finding the slope of a secant line between two values, but it is sort of the same setup. We're saying, okay, the average rate of change would still be r of theta 2 minus r of theta 1. That's still the change in the outputs. I would rather say it like that instead of change in y, over the change in the inputs. All right. And on a graph, it's a little harder to see like what's happening there as far as your average rate of change, but we won't have context to these. So we will still say that r is on average increasing or decreasing on an interval by approximately some number of units per radian. This will have no context. It will always be units per radian. All right, so if we have this formula in our brain, average rate of change is pretty easy. So find and interpret the average rate of change over this interval. So, all right, we're using these 2 points. I like to circle them if I'm given a table. The average rate of change is equal to r of pi over 2 minus r of pi over 6 over pi over 2 minus pi over 6. R of pi over 2 is negative 3 minus this quantity, negative 2 radical 3, all over pi over 2 minus pi over 6. So that's 3 pi over 6 minus pi over 6. So that's 2 pi over 6, which is pi over 3. We are expected to simplify this stuff, so careful with your negatives. Negative 3 plus 2 is negative 1, and then we're going to get plus radical 3 over pi over 3. And you need to know, we've dealt enough with rational expressions, whether it was trig or algebraic. You need to know that you can say that's the same as 3 times negative 1 plus radical 3 over pi. Get rid of the complex fraction by multiplying by the reciprocal. So here's the average rate of change. All right, I need to interpret that. On average, the radius, or you could just say r, but I already started writing the radius is this positive or negative? Let's see, negative 1 plus 1 point something is positive, times positive 3 over pi. So it's increasing by 3 times negative 1 plus radical 3 over pi units per radian. Remember, not really any context besides the fact that it's always going to be per radian, because that's the input. Is the polar graph getting closer to the origin or further from the origin on the interval above? So we're looking on the interval pi over 6 to pi over 2. How do we decide closer to the origin or further from the origin? Remember, we look at the sign of r. So on this interval, in both cases there, r is less than 0. And is r increasing or decreasing on that interval? So you're going from negative 3 point something to negative 3. You're getting closer to 0. So r is increasing. And so those are acting against each other, right? You have r being negative, but r is increasing. So that means that the graph is getting closer to the origin, which is 0, 0. Use the table from problem 5 and interpret the average rate of change over this interval, pi over 2 to pi over 7. So again, the average rate of change is equal to r of pi minus r of pi over 2. It's a good idea to always write this formula because it gives you sort of a grounding of what to do. So r of pi is 7 minus negative 3 over pi minus pi over 2 is pi over 2. Again, simplify this. It's not 10 over pi over 2. It's 20 over pi. 10 times 2 over pi. So there's the average rate of change. Interpret that. So on average, r, I'll just say r this time, or the radius, this is positive, so increasing by 20 over pi units per radian on this interval. At theta equals pi, which is in this interval at the end, right? Is the polar graph getting closer to the origin or further away? So we need to look at this. Okay, r of pi was equal to 7, which is greater than 0. So r of pi is positive. And what's happening with the graph? Or what's happening with r's behavior? Excuse me. R goes from negative 3 to 7, so that's an increase. But then 5 minus 2 radical 3 is a decrease. So r of pi is positive, but r of pi is a relative, what is that? A relative max? because the graph goes from R goes from increasing to decreasing. So because of that, it would be neither. So the graph isn't closer or further from that point to the origin. Basically, that's a turning point. It's kind of like saying, what's happening? You've hit the brakes and you're stopped. You haven't, or I'm sorry, this is like before you've hit the brakes. You're not accelerating and you're not decelerating. You're just stuck right there for a second. All right. Last thing to learn. So this is something we do all the time in calculus. So we're introducing you here. So use the average rate of change to approximate the value of R at a given angle. So we don't have R, so I can't just say what is R of 5 pi over 18. But I can first find the rate of change. So let's start there. Find the rate of change, average rate of change. So again, that's R of pi over 3 minus R of pi over 6 over pi over 3 minus pi over 6. R of pi over 3 is negative 3 minus negative 2 over, let's see, this is 2 pi over 6 minus pi over 6, so that's pi over 6. Instead of negative 1 over pi over 6, let's make it negative 6 over pi. So here's the average rate of change. So this is R is the average rate of change means that R is decreasing on average by this much. Okay, now use the table and the average rate of change to approximate this value. So again, we do this in calculus all the time in the beginning of the year too. So here we go. If I want to approximate R of 5 pi over 18, I can use a linear equation because this is a slope, right? Average rate of change is a slope. So we're saying, well, let's approximate it by using one of the values we know. So you want a point that's close to 5 pi over 18. Although I suspect that you could use either one on an AP test. But let's see. Pi over 6 is 3 pi over 18. And pi over 3 is 6 pi over 18. And I'm talking about 5 pi over 18. So I want to pick the closer point. Let's jump off from R of pi over 3. What are we going to do? We're going to add to that the average rate of change times the change in x. How far is it from pi over 3 to 5 pi over 18? Well, we'll figure that out in a minute. We just would subtract. Our starting point wait, 5 pi. Yeah. Our starting point, sorry, I didn't want this to be negative. Starting point minus our approximation, 5 pi over 18. All right, so what does that mean? It means that we're saying, well, we would have negative 3 minus 6 over pi, that slope, times how much of a change are we making? 6 pi over 18 minus 5 pi over 18 is pi over 18. So that's negative 3 minus 1/3. So negative 3 1/3, or what would this be? Negative 3 1/3. Well, I'll just keep it mixed like that. Or negative 10/3, I guess. Okay, so we could say that. Excuse me. If we do the other points, we would get something slightly different. I think we would get negative 2 2/3. So it might just depend, but that's my approximation for 5 pi over 18. And what you're doing there is just saying, okay, here's a starting point. I'm going to travel the slope over this certain number of points, and I'm going to land right here. And that's my approximation for what the value is. Maybe the actual value is like down here or something, but I'm going to approximate it that it's close, it's right here. So again, we do that in calculus all the time. It'll always be one point you're given plus the slope times the difference in your inputs. All right, I'm going to stop there. Oh, you know what? Wait, did I subtract in the wrong order though? Sorry. Pi over 3. This is 5 pi over 18. Yeah, sorry. This would be negative. This would be plus. So make this negative 2 2/3. Sorry, or negative 8/3. All right. So actually, I guess in this one we do come up with the same thing. I think if you put in pi over 6, you also get this. The order of subtraction matters there, right? Because it's always b minus a. So I put that in wrong. All right. That finishes our new content knowledge for AP Pre-Calc. So that's it. From here on out, we're going to practice this a little bit. We'll have a test over this chapter. And then when we come back from spring break, we will be officially in review mode. So congratulations.